So I heard that the Chem 163 students are covering enthalpy and entropy right now, so it's perfect timing. We're going to start off chapter 6 by reviewing enthalpy a little bit. Does anybody remember what enthalpy is a measure of? Not randomness. Oh boy. All right. It's a measure of the amount of heat. Released or absorbed. Oh. By a reaction. Assuming that you've got constant pressure and volume. So assuming that you're not changing the pressure or volume, you can measure the amount of heat being absorbed or be released by a reaction. It's a really important concept, right? Oftentimes in chemistry, we measure this as delta H. What does delta stand for? Change in enthalpy. So if your change in enthalpy is a positive value, what does that tell you about the reaction? Is it releasing heat or absorbing heat? It's going to be absorbing heat. So absorbing heat. All right. Conversely, if you've got delta H that is a negative value, what does that tell you? It releases heat. All right. What do we call a reaction that absorbs heat? It's going to be endothermic. This is exothermic. There's endergonic and exergonic too. That's something entirely different than this. And we'll talk about that. That's related to Gibbs free energy, not enthalpy. All right. So the question is, how do we measure this in lab, or how do we measure it if we've got a textbook? The easiest thing to do is to pull up a bond dissociation energy table, which is found in your textbook. These are standard values. So they're all normalized, and there's a bunch of different bond types. I tell students that this is really similar to the pKa table that we're looking at. You might not find a perfect match, but your goal is to find the closest possible match that you can, right? All right, so you can estimate delta H values by using bond dissociation energies. So let's take an example of this. The easiest thing to do is to make a list of bonds made and broken. All right, so let's take an example reaction. And in this example reaction, I'm going to take this molecule, propane. I'm going to react it with elemental bromine. I'm going to use UV light to initiate the reaction. So that's just a symbol for UV light. And when you do this, you can actually halogenate that center carbon. And your byproduct is hydrobromic acid. All right, so on the left-hand side, I'm going to make a list of bonds broken. And over here, I'm going to put bonds made. And let's try to come up with a good list. So let's start with bonds broken. What's the first and most immediate one that's clearly broken in this reaction? BR, okay? So I'm just going to go ahead and say we're cleaving this bond between two bromine atoms. All right, what's the other one? Carbon hydrogen. Sometimes people forget that in this reaction, that blue hydrogen right there is no longer there. So we're losing one of those carbon hydrogen bonds. So if I look at this one, there's a few different ways we could write it. We could write it as is. However, we could also use partial condensed formula and say, all right, we're cleaving this bond. That carbon also has a second hydrogen, and that has two methyl groups coming off of it as well. All right? Does that make sense? So the red line indicates that we're cleaving that specific bond. All right? Now let's think about bonds being made. What are we making? HBr, right? That was a new bond that wasn't present to start out with. So we'd say H getting bonded to a Br was a new bond that was being made in this reaction. All right. The other one that was being made is the bromine to carbon bond, right? So we could say bromine that's now bonded to the CH that also has two methyl groups. And so we've got a comprehensive list of all our bonds broken in this reaction and bonds made in this reaction. All right, conceptually, when you break a bond, does it take energy or release energy? So when you break it, it takes energy to rip that bond apart, right? So should the sign be positive or negative for bonds broken? Positive. You're inputting energy into the system. So the sign for bonds breaking will be positive. You have to input energy to break a bond. All right? Conversely, when you make a bond, that is energetically favorable. So the sign for this will be negative. It'll release energy. All right, so now let's go up to our table and try to find these values. Let's find the bromine-bromine. So when I go up and I look for that one, I can see it right here. So bromine to bromine. Let's try to stick with one unit type. I really prefer kcals per mole, although if you talk to a physicist, they would disagree with me strongly and they'd say you need to do kilojoules per mole. Chemists and physicists disagree all the time. Just pick one and be consistent with it. I'm going to pick kcals per mole just to be controversial. So it's 46. So positive 46 kcals per mole. All right, let's do the next one. So we need to find a hydrogen that's bonded to a secondary carbon. So let's go back up and we'll look for that one. So in this case, we're trying to look for this compound right here, right? That looks exactly the same. So that's 95 kcals per mole. All right, so we've got one half of our list done. Let's do the bonds made side and look for HBr. So if we go up and we look for HBr in here, I'm going to erase these. HBr is down here, 88. So let's plug that in. And it's important to remember the sign, right? It's got to be negative 88 kcals per mole. All right, and then our last one is bromine bonded to a secondary carbon. Let's look for that one. So when I'm looking for looking for this one, it looks like it's 68. I know it's kind of hard to see, but you can always pull up this chart in your book. It's table 6.1. It's pretty good. You can also look on Wikipedia if you want. They've got a pretty extensive table as well. So this is 68 kcals per mole. However, we need to put negative 68 to account for that sign. All right, so now we've got a comprehensive list of all the bonds made and broken in this reaction along with their bond dissociation energies. Okay, now what we need to do is find delta H naught for the reaction. So the standard enthalpy change for this reaction. The easiest thing to do to find this is to basically add up all of your bonds that were made and broken. Okay, so if we go ahead and do some pretty sophisticated mathematics, we can work through this. We're going to add all of these together. We're going to do 46 plus 95 minus 88 minus 68. And if I go ahead and I plug this all in, I'm getting negative 15 kcals per mole as my final answer for this reaction. So is this reaction endothermic or exothermic? Exothermic. The overall sign of the reaction is negative, which means it's releasing heat, right? So let's make a note of that. reaction is exothermic, since the sign of delta H is negative. Does that make sense? All right. Delta H is really interesting. Does delta H tell you whether or not a reaction will be spontaneous, though? No, not at all. There's other important factors we need to consider when we're looking at whether or not a reaction is spontaneous. What's the other half of the coin? Anybody remember? Close. Entropy, right? So it's entropy and enthalpy, two sides of the same coin. Both are super important for determining whether or not a reaction is spontaneous. So let's make a note of that. Delta H on its own is not a good predictor of a reaction's spontaneity. We must know about entropy. Does anybody remember what entropy is? It's a measure of disorder in the system, right? So we need to know about whether or not during the reaction your reagents are getting more disordered or less disordered. That is also very important for knowing what's going on. So let's review entropy a little bit. And like I said, it's a measure of disorder. All right. And again, physicists and chemists disagree a little bit on this, so I'm going to approach it from the chemistry side. Chemists like to view the system, not the universe. So we're going to look at delta S of the system. And if delta S of the system is positive, that means that you have more disorder after your reaction's completed, right? So maybe you start out with 1 mole of something going in and you get 2 moles of products coming out. You're creating more disorder, more chaos in the system. All right? Conversely, if you have delta S of your system is negative, that means things are getting more ordered. Does anybody know which one the universe tends to favor? More disorder, right? I don't know if anybody's played Cards Against Humanity. One of my favorite cards is the inevitable heat death of the universe. And that really gets back into the idea of entropy wanting the universe to basically get more and more chaotic and expand out at an accelerating rate. Pretty crazy idea, but it's important to remember whenever you get stressed out. We'll all die and the universe will die too, right? All right. Yep.
So, of course, you know, whether or not you have 2 moles versus 1 mole, but the size of these molecules, how does that factor in?
Yeah, so the question was, what about the size of the molecules, not just the moles? We'll come back and we'll talk about that. So moles are just part of the factor. You also have to consider degrees of freedom as well.
What's the real gas law?
What's that?
The real gas law where it puts it in the molecular force and point particles?
Yeah, so the gas law is an oversimplification that works pretty well, but isn't 100% accurate. Yeah. All right, so let's come up with an easy way of predicting this. The sign for delta S of the system. All right, so let's do this. More moles of product than reactant. What does that likely mean? Is delta S of the system going to be positive or negative? I'd say it's more disordered, right? We're making more moles of product, so it should be positive. So delta S of your system will be positive. Conversely, if you have more moles of reactants than product, your sign must be flipped, and delta S of your system would have to be negative, right? So this one is pretty easy to do. Yeah?
How does that work with things that don't fully react?
So if something doesn't fully react, we're only accounting for the things that do react in that reaction. Good question, though. All right, so this is pretty standard, pretty easy. I'm not going to expect you to dig up a table or anything like this. I'll just want you to know the overall sign being positive or negative. The question is, well, what do you do if there's a tie in your reaction? What if the same number of moles going in come out of the reaction? If that's the case, you have to go to a tiebreaker rule. And the tiebreaker rule is pretty easy to remember. It has to do with freedom of motion. If you have more freedom of motion, meaning you can flail about wildly as a molecule, that means you're getting more chaotic, right? That means delta S of your system is going to be positive. And I'll show you an example of this. Oops, I forgot my E. But let's do this other one first. If you've got a decrease in freedom of motion, delta S of your system must be negative. So let's take an example of this using a reaction that we'll cover later this year. And I want you to help me predict the sign. So we've got something called a diene. So it's a molecule with two alkenes in it. We're going to react this with another alkene called a dienophile, meaning it wants the diene. It's a good Halloween joke. Nobody got it, though. It's okay. And when you react this, you can actually form a ring system. Is delta S of the system going to be positive or negative? Okay, so let's think about this. It looks to me like we're going from 2 moles to 1 mole. So it looks like we're getting fewer moles of products than reactants. That means delta S of the system must be negative. All right, now let's do a harder one. All right, in this reaction, we've got an oxygen with a positive charge. And what will end up happening is this bond will break and dump both bonding set of electrons to that oxygen. So we haven't gained or lost any atoms during this. If we look at this one, we'd say, well, we're going from 1 mole of starting materials to 1 mole of products. So it's a tie. Do we have an increase in freedom of motion or a decrease in freedom of motion? Increase. So this is more floppy. That means we're increasing our freedom of motion. So delta S of this system would have to be a positive value. Does that make sense? Entropy is pretty tricky to measure, though. Entropy is closely related to another variable, and what is that? Anybody remember? Think about if you want to make molecules get more and more disordered, what can you do to make that happen? Heat it up, right? So if you heat things, they tend to get more and more disordered. So entropy is super closely related to temperature. So what we typically have to worry about in a reaction is the temperature that the reaction's being done at, whether or not it's getting more ordered or more disordered, and whether or not the reaction is exothermic or endothermic. We have to pay attention to all three of those variables. All right? And that brings us to the next point that ties them all together into one common unit. Yep?
So, how do you know that it doesn't on the right?
Yeah, that's a good point. So you're wondering about why I use the term floppy. What I always tell people, this is kind of a weird analogy, is imagine you're handcuffed, right? You're forced into order, right? You can't flail your arms about. But if you take those handcuffs off, you can flop your arms around. You have an increase of freedom of motion, right? So you're getting more disordered without the handcuffs on. So typically molecules, when they're forced to cyclize and form a ring, you're forcing them into a more ordered fashion. But if you're breaking that ring open, they're more floppy and there's more disorder. Yeah. All right, so let's talk about how we can relate enthalpy, entropy, and temperature. Does anybody remember what that unit is? Gibbs free energy. You thought you got away from this in Gen Chem, but no, it's back. All right, Gibbs free energy shows up in organic chemistry, and it's the measure of spontaneity for a reaction. All right, and if you remember, the easy thing to do is say delta G equals delta H plus negative T delta S. Depending on the textbook or teacher that you had, they may have shown this as just simply delta H minus T delta S. It's the exact same thing, right? But you'll see why I'm separating it out later. It makes doing some of these tricks a little bit easier. All right, so this is the change in Gibbs free energy. This is your change in enthalpy. This is your temperature in Kelvin. We don't use Celsius for this value typically, unless Celsius is included in your entropy unit. And then delta S is your change in entropy. All right, so let's say hypothetically we have a spontaneous reaction. Does that mean the reaction is going to occur fast?
No, not necessarily.
Not necessarily. So the example I like to use is I am spontaneously turning to carbon dioxide and water, right? Hopefully that won't happen for another 60 plus years, I'm hoping. But I'm spontaneously converting myself into CO2 and water. Spontaneity has nothing to do with how fast a reaction occurs. It just says eventually, even over a millennia, maybe this reaction will start to occur, right? So over time, the reaction will happen. All right? So let's take a look at how chemists like to represent this. And we like to show this using reaction coordinate diagrams. No, this is not a dice scale. This is essentially a free energy relationship, so showing potential energy for a reaction. All right, so on one scale we've got energy, and on the other we have reaction progress. And maybe you've got your starting materials that have some potential energy to them, right? There's always energy stored in bonds, so anytime you have starting materials, they've got some potential energy there. All right? And let's say you've got products that have less potential energy. Do you think this reaction will be spontaneous? Another way of thinking about this is if you park your car in neutral at the top of a hill, your car will want to roll down that hill and have less potential energy, right? So this would be an example of a spontaneous reaction. All right? This is a little confusing, though, because students will sometimes think, hey, is it just a straight line from your starting materials to your products? No, sometimes that car, in order to get it to roll down the hill, needs a little nudge, right? So you've got to apply some energy to get a reaction to go. This is called activation energy. So when we look at this, we kind of cut our hill in half. The hump that you have to go over, this is called your activation energy. Sometimes you have a large amount of activation energy. Sometimes you just need to barely nudge the car and it will roll down. That size of the hump can vary. Conversely, the net drop in energy is called your Gibbs free energy, or just delta G. So it's your change in Gibbs free energy. So this is a spontaneous reaction. This is also called exergonic. All right, let's compare the alternate example. So we've got energy over here. We've got reaction progress over here. Maybe in this one, we've got starting materials down here, and we're making something that's less stable. Same idea. Oftentimes you have kind of a hump. However, it does get a little bit weird, so I'm going to cut that hump in half. The net change in energy levels is still delta G. All right, and then if you think about the activation energy, is the activation energy going to be this hump shown in blue or this hump shown in green? Green. It's the overall hill you have to climb before you start going downhill, right? So the green arrow would be more appropriate. So let me erase this, clean it up, and say this is your activation energy. All right, so if we think about this, right, in order for this to be spontaneous, your car would have to magically crawl itself up a giant hill, get back into that little well on the product side. But we know cars don't do that. Cars would prefer to go down a hill, not up a hill. So delta G tends to prefer going in a downward direction, not an upward direction. So this would be a non-spontaneous reaction. This would be endergonic. In general, net reactions aren't non-spontaneous, but you may have steps in reactions that rely on a non-spontaneous step, and we'll talk about multi-step reactions a little bit later on. Does that make sense? All right, so now let's take a look at a weird example. A reaction was run where delta H naught was found to be a negative value and delta S of the system was found to be a negative value. Is this reaction spontaneous? So let's try to piece this apart. And what we'll do is we'll rewrite our Gibbs free energy equation. So delta G equals delta H plus negative T delta S. And what we can do is we can plug in some of these values, right? So we said that delta H is a negative value. Okay, we're going to take a negative value and then we're going to add it to this whole set in green, right? Because entropy is tied into temperature. All right, so negative T times delta S will be what? Positive, right? So negative times a negative is always going to be a positive. So we can plug this in. All right, so delta G, is it going to be negative or positive? You don't know, right? It's kind of a weird example. So what do we need to know more about? Temperature, absolutely. So let's kind of explain that. If the temp is low, then delta G is going to be what? It's going to be negative, right? Because if temperature is really low, that negative T delta S portion of the equation is going to be pretty insignificant. It's going to be a very small value, right? So if the temp is low, then delta G is going to be negative, and the reaction will be spontaneous or non-spontaneous? It'll be spontaneous. All right. If the temp is high, then maybe that positive side, that negative T delta S side of the equation will be a very, very big number, and it will overtake the negative value from delta H, and delta G could be positive, right? All right, and this is confusing for chemistry students. I used to see this in graduate school when we would get new chemists in the lab, like first year grad students. They'd say, my reaction isn't working. I'm just going to crank up the heat and try to get it to go faster. And I'd be like, no, no, no. Let's look at delta G, because sometimes you're actually doing more harm than good by heating up a reaction. Some reactions are actually more favorable at lower temperatures than they are at higher temperatures. You have to consider the entropy factor of that equation, right? So don't always assume that applying more heat will make a reaction more spontaneous, or assume that it will make it go faster. You have to be very, very careful with that. All right, so tomorrow when we come in, we'll look at equilibria, but spend some time thinking about the pod, and you may need to pull up the table from your textbook to solve that pod.